Now using this step response, let us see how we can find out the response to a general input. Response to a general input xt in terms of step response. Now, if x of t is the general input, ys will be hs times x of s is the fundamental rule that we are having. But h of s is s times a of s. So I can write this as s times a of s times x of s. That's what we are having. I can write this as s times x of s times a of s. Now, y of s therefore is the product of two Laplace transforms, s times x of s and a of s. The time function corresponding to this is the initial response at. What is the time function corresponding to this? Is dx by dt, the derivative of this, taking into account that starting from t equals 0 minus. Therefore, yt can be written as x prime t. When you take the derivative of x prime t starting from t 0 minus, that is, if xt is like this, this is x 0 minus, this is x 0 plus. When you are taking the derivative, you must take this transition also into account, and that is the meaning of this. X prime t considered from t equals 0 minus onwards, convolved with a of t, which is the inverse Laplace transform of that. Now you note that x prime t, if this is the variation of x of t, this is xt, x prime t can be written as, in the jump 0, x 0 minus is 0 because we always talk about causal inputs. So the causal input 0 is jumped to 0 plus, therefore the derivative you get x 0 plus times delta t plus the rest of the derivative taking starting from t equals 0 onwards, 0 plus onwards. So x prime t starting from t equals 0 minus can be thought of as an impulse function which comes because of this jump plus the derivative from t equals 0 onwards. So I can write this further as x 0 plus times delta t, this convolved with a t, plus x prime t, which we consider only from 0 plus onwards, convolved with a t. That is what we are having. And we earlier observed that any function of time convolved with a delta t means is equal to the same function itself. Convolving with delta t does not change the function. Therefore, I can write this as x 0 plus times a t. This you can also visualize easily because the Laplace transform of delta t is 1, the Laplace transform of this is a of s, then the convolution as a Laplace transform 1 times a of s, the inverse Laplace transform gives us back a of t, plus x prime t for t greater than or equal to 0 plus convolved with a t. So this is the result that we get. Now let me put this down in the form of integrals more explicitly. So what we have here is yt therefore is x 0 plus times at plus this one I will put in the form of an integral starting from 0 plus to t x prime tau a t minus tau d tau. That is what you are having. That is the meaning of that. That means your response to any arbitrary input xt can be obtained if you know the initial response or the step response. You can find it out in this manner. This comes from, of course, from this Laplace transform SAS times x of s. Now one can also alternately, let us have some, first of all before that the physical meaning of that. I will just briefly outline without spending too much time on that. Suppose this is x of t. You can think of this x of t as a step function to start with. This is x0 plus times u of t plus a number of small steps occurring later on at different values of time, and each of these steps will have something related to x tau, delta tau, something like that it will be there. So we have the given x of t can be decomposed as a number of steps starting with x0 plus ut, and subsequent steps will have a height depending on the derivative and the interval that you are taking. So each one of those x prime t delta tau is the height of the step, and that occurs at a point tau. Therefore it brings forth a delayed step response. So summation of all those things will be represented by this integral, and the response to the initial step is represented by this term. So that is the physical significance of this particular formulation of the output in terms of the initial response. So this is the physical significance of this. Now if there are impulses in the step response at the origin, suppose A of t has an impulse at the origin, to take that into account you can put this as t plus to take into account impulses. Maybe I'll write this separately, because instead of structuring the picture you can say upper limit taken as t plus to include impulses at the origin, if any, in AT. So it is possible that the step response may include an impulse at the origin. To take that complete impulse into account, the upper limit is taken as t plus. An alternative version after all, I associated this s with the x of s. I could have taken associated s with as instead of x. So that means I could have written xs times s times a of s. So an alternative version would be yt will be a0 plus times x of t plus 0 plus to t plus a prime tau x of t minus tau d tau. So that is an alternative way of representing this, because after all xs is symmetrical in as and xs. So whatever role xt plays here, at can also play here. So these are alternatives. Now these two integrals that we have here are also referred to as superposition integrals in literature. They are also referred to as Duhamel's integrals. So these are alternative names for that. Even the convolution integral in terms of impulse response is also called superposition integral, but in literature this is also called superposition integral. These are all superposition integrals, Duhamel's integrals. Duhamel's integral is of course particularly with reference to the step function. Another property of the system function that we would like to make a note of is the significance and poles and zeros of HFS. So HFS is a rational function, as I mentioned, is a ratio of two polynomials. Therefore it is ratio of GS over FFS. So it is in general there is a constant multiplying factor and product of several such factors summed on I, and in the denominator we have products of such factors summed on I. And the set Zi are called the zeros of this HFS, and the set of Pi values are called the poles of this, something which I think I have already mentioned. So HFS is uniquely specified by the locations of zeros and poles as well as the constant multiplying factor m. So the poles and zeros are generally represented in the complex plane by the Z locations. The Zi locations are indicated by zeros, pole locations by crosses. And it has to be kept in mind that since GFS and FFS are polynomials with real coefficients of s, whenever a complex pole occurs, its conjugate also must be present. Similarly, a complex zero is always accompanied by its conjugate. That means complex zeros and poles occur in conjugate pairs, not singly. As far as the real poles and zeros are concerned, there is no problem. It can appear with unit multiplicity. Now, an important factor that one would notice in solving a system is, suppose you have different types of outputs that you are looking for, and naturally you have different system functions relating the different outputs to the corresponding input. It turns out that suppose you have h1 of s, h2 of s, h3 of s, depending upon the y's that you are talking about, y1, y2, y3, all of them have got the same f of s in the denominator. So f of s equals 0 is what is called the characteristic equation of the system. This is a characteristic of the system. So no matter what response quantity you are looking for, the denominator here f of s is the same for all transfer functions, for all system functions, for a given system. This is called the characteristic function equation. And when you talk about y of s here, your h of s times x of s, and you make the partial fraction expansion of this in y of s, then the partial fraction expansion of y of s will involve terms containing poles of h of s, terms involving poles of x of s. In the partial fraction expansion, what you have is terms containing poles of h of s are represent the natural frequencies of the system. They are the PIs here. They are the roots of the characteristic equation. So the natural frequencies of the system are the roots of the characteristic equation. When I talk about natural frequencies, I am talking about frequencies in the complex domain. They are the the roots of the characteristic equation. They are the poles PI. On the other hand, your the terms containing poles of h of s, x of s are the forced frequencies. They are the frequencies that come as a result of the particular input. So when you have got y of s, when you make the partial fraction expansion, you get some terms corresponding to the poles of h of s, some terms corresponding to the poles of x of s. The terms corresponding to the poles of x of s, if you add up the time domain response of all of them, this is the forced response. On the other hand, if you take into account only the poles of h of s, they represent the natural frequencies. So the summation of all the corresponding time domain expressions represents the natural response of the system. And the total response is what you obtain when you take the inverse Laplace transform of this. So whenever you want to segregate the total response, its natural response and forced response, you can always look at this as emanating respectively from the poles of h of s and the poles of x of s respectively. As far as the zeros are concerned, they don't have any particular connotation like this. They only vary the amplitude of these various components. Suppose I have one particular response quantity is e to the power of st a. It is the amplitude or the multiplying factor of the complex frequency term that is dictated by the zeros. The poles, however, represent the modes, the time expressions, the complex frequencies that are dictated by the poles, whereas the zeros will only vary the amplitude of the various terms. So in this lecture, what we have done so far is acquainted ourselves with the definition of the system function in terms of the Laplace transforms, You recall that system function is defined as the Laplace transform of the response quantity to the Laplace transform of the excitation quantity with 0 initial conditions prior to the application of the input. And the system function in general is a ratio of two polynomials for the type of system that we are talking about, lumped parameter systems, which is f of s, g of s over f of s. And we looked at various properties of the system function. The system function is the Laplace transform of the impulse response. We also saw the system function is also related to the Laplace transform of the step response. We saw the various types of convolution integrals, how to get the general output for the general input in terms of the impulse response h of t or the step response a of t. We also finally looked at the nature of h of s as a ratio of two polynomials which specify the locations of zeros and poles in the complex plane, and we mentioned that the poles of the h of s indicate the natural frequencies of the system. They are invariant for a particular system, and whatever the type of output that you are looking for in that system, they do not depend upon the input quantity. On the other hand, x of s will have some poles which are characteristic of the particular excitation function that you have dealing with at the point of time. So y of s, which is the product of h of s times x of s, will have poles partly coming from h of s and partly coming from x of s. The poles coming from h of s represent the natural frequencies, and the associated response is the natural response. The poles coming from x of s are the forced frequencies, and the associated time response is the forced response. More about the system function will be taken up in the next lecture.